All right, let's get started. So today we're going to talk about meta-learning, and then if I get through that before the end of the lecture, I'll also talk about parallelized reinforcement learning algorithms. So a few class notes. Now less than 2 weeks until the project milestone, so do make sure you get started on your final project. And starting next week, we'll actually enter into the final phase of this class where we'll actually just have guest lectures. We'll have researchers working on reinforcement learning coming in and talking about their research. So we'll have one more lecture on Monday, which will probably be by Abhishek Gupta, and then I'll do also part of the lecture there. And then starting Wednesday, we'll have our first guest lecture, which on Wednesday will be Igor Mardach from OpenAI. So for the guest lectures, those of you that are watching online, it'd be really great if you guys can come in person. For the guest lectures, it's a lot of fun to come in person, ask the speaker questions, get to meet them and so on. So do come in. Yeah, so that'll be starting Wednesday next week. So today I'll talk about meta-learning algorithms, and then I'll conclude our discussion of transfer in DeepRL. And then if I have time left over, I'll also talk about parallelism. OK, so just to put the roadmap back on the board there, we had three classes of transfer learning methods that we were discussing. The first is forward transfer, where you have a source domain, and you'd like to use something from the source domain to succeed on a target domain, maybe with less experience or more quickly. We talked last time about multitask transfer, where you have many different source domains, maybe different source domains where you're trying to do different things, and you'd like to transfer some kind of knowledge from there into a target domain. And today we'll talk about a slightly different multitask setting called meta-learning. So let's discuss that a little bit. And again, just like before, the disclaimer is that there's no single solution. So here, at this point, I'm really just presenting very recent results from the literature. And a lot of this is kind of research that's still underway, where we haven't fully answered the questions and fully figured out what exactly is the best method for each of these things. OK, so forward transfer, that we had one source domain and one target domain. And there we saw that essentially diversity is good. So the more varied the training is, the more varied the source domain, the more likely you are to successfully transfer to a target domain. And with multitask learning, we saw that we get even more variety. The trouble is that now we're no longer training on the same task for all of our source domains. So now we need to do a little bit of extra work to compensate for the fact that the policies might all be doing different things. But still, more variety means more likely to succeed at transfer. In all these things, we have to figure out how we represent the knowledge that we're transferring. And we can represent it, for example, using a model. If we're doing model-based RL, this was something that we talked about for multitask learning in particular. Instead of trying to transfer a behavior, instead of trying to transfer a policy, well, let's figure out sort of the underlying governing laws of physics of that environment and transfer those, because those are likely to be conserved across tasks. We talked about how we could transfer policies, which oftentimes requires some kind of fine-tuning, but is maybe a little closer to what we want to accomplish because there's a lot of knowledge contained in that behavior. But what about transferring knowledge about learning methods themselves? What if there's something that you can figure out from past tasks that you've seen that doesn't necessarily tell you how to accomplish a new task, but tells you something how you can figure out a new task? So that's what we're going to talk about. So meta-learning basically deals with this kind of problem. If you've learned 100 tasks already, can you figure out how to then learn the 101st task more efficiently by using the experience of learning? So hence meta-learning. So now having multiple tasks is actually a huge advantage. Now we're not really so concerned about the fact that all these different tasks have a different goal. We're actually happy about that because now we can figure out from all these different tasks what are the kind of learning strategies that seem to generalize most effectively, the learning strategies that are useful for all sorts of different tasks. So meta-learning refers to learning to learn. And in practice, it actually ends up being very closely related to multitask learning. And I should mention a little caveat here, which is the term meta-learning is actually used in two slightly different ways in the community. So in the deep learning community, people often use meta-learning to mean learning to learn, and that's what I'm going to talk about in this lecture. Sometimes you'll hear the term meta-learning as being used to be synonymous with meta-optimization, which is a very closely related thing, but not exactly the same. So meta-optimization refers to, for example, having an algorithm that automatically tunes hyperparameters or learning rates. Very closely related to the kind of meta-learning I'll discuss here, but in a very subtle way different. So in today's lecture, I'm talking about this kind of meta-learning, the learning to learn, not exactly the same as meta-optimization, but very, very related. Okay, so there are many, actually, formulations of this kind of meta-learning problem and also many different kinds of solutions. And we can broadly categorize them, and this is a very coarse categorization, into 3 categories. Learning an optimizer, which you can think of as basically a function that looks at the current parameters of the network, looks at how well it's doing on a particular task, and tells you this is how you should change your parameters to do better. So this is a very literal kind of meta-learning approach. You can formulate it as, and we'll get into a lot of these in more detail, well, you can formulate it as learning a recurrent neural network that actually ingests a data set that ingests some experience. So you can have a recurrent neural network that basically reads in a data set and then makes a prediction on a test point. So then it's not explicitly learning an optimizer, but one might imagine that within the recurrent structure of that network it's doing something that looks like learning. So we'll discuss that more. And then the third one, which is a little bit interesting, is learning a representation. And we'll actually talk about how learning a representation could be viewed as a kind of meta-learning. This one is a lot less obvious when you first hear about it, but we'll see later in the lecture that this actually makes a lot of sense. And there's a little cartoon that I wanted to show you. This is from Kay Lee, who's a student, a PhD student here at Berkeley, that illustrates, this one actually illustrates the first class, the learning and optimizer type meta-learning algorithm. But I really like this cartoon because I think if by the end of this slide the problem formulation is not clear to you, I think the cartoon really helps clarify it. So in the top, here you can see kind of a standard gradient descent optimizer, and the gradient descent optimizer is in this valley, and he says, well, I'm going to follow the gradient, and I'm oscillating because I'm in a valley and I don't know what to do, so I'll just keep oscillating and have trouble converging. So if you were a person watching this learning algorithm, you might see, oh, my learning rate is not going down, or my error is not going down, so maybe I'll reduce my learning rate manually, and that might get it to stop oscillating. But if you have a smart meta-learner, so here, it's a little hard to see on the slide, but this is actually a little red ball, and this is a ladybug. So the presumption here is that the ladybug is a lot smarter than the ball. The ball is just rolling downhill, but the ladybug is smart, and the ladybug thinks, oh, I've seen this kind of situation before, and last time I saw myself oscillating like this, what I needed to do was sort of damp myself out, reduce the oscillations, and very neatly glide into this valley here and find the optimum. So if you're the ladybug rather than just a ball rolling around under the force of gravity, then you can be smart and use your past experience of having seen these kinds of situations in the past to optimize successfully. So this is the cartoon that illustrates meta-learning. All right, why is meta-learning a good idea, and specifically a good idea for us in this class to know about? Deep reinforcement learning algorithms, especially model-free deep reinforcement learning algorithms, usually require a very large number of samples. And all of you saw this in homework 3. If you did homework 3 successfully, that very likely means that you ran your Q-learning algorithm on Pong for at least 1 million, hopefully 2 million frames, and got it to do a pretty good job. But that's quite a lot of frames, and you probably had to wait quite a while to get that. And if you were running this not in a simulator of the Pong game, but let's say on a robot trying to actually play tennis or something like that, well, that would have taken you a very long time indeed. So this is maybe a little bit troublesome. If we can meta-learn a faster reinforcement learner, then maybe we can learn new tasks much more efficiently. So maybe it's too much for us to hope for that we can build the perfect reinforcement learning algorithm that can just solve new tasks from scratch instantaneously. I mean, even people can't do that, right? When we're born, we can't immediately, jump on a bicycle and ride the bicycle. We have to grow up. We have to learn about how to move our bodies, how the world around us works, and so on. So maybe it's too much to hope for to build a perfect reinforcement learner, but maybe we can have a reinforcement learner that learns to learn more efficiently from past experience. So it'll still require lots of experience, but now, after having collected that experience once, it'll be able to solve new tasks much more quickly. So what can a meta-learner do differently? Basically, the idea hopefully kind of makes sense. You can learn to do better, but what is it that you can actually do better? What are your kind of the levers that you can pull to do better than a naive learning algorithm? Well, in a reinforcement learning setting, you can explore more intelligently. So one of the things you could do is you could avoid trying actions that you know to be useless. If you imagine that you're, let's say, controlling an autonomous vehicle, well, probably crashing that vehicle into walls is just never useful, regardless of what you're trying to achieve. So you can figure out that these kinds of exploratory behaviors are not useful, so you can explore more intelligently. You can acquire the right features more quickly. So you can figure out that there are certain parts of the input space that you should pay more attention to, even though they might be different across different tasks. Those are the things from which you can extract the right kinds of features, so you should spend more time learning from those. And there are a few other things you could do here. So let's first talk about meta-learning in a supervised learning setting, because there it's quite straightforward to build up a little bit of intuition for how such algorithms might work and to present a few relatively simple approaches. I'm not going to talk about really the state-of-the-art approaches for meta-learning and supervised learning. I'll just illustrate a few simple examples just to build up our intuition and then dive into meta-learning for deep RL. So this is an illustration from a paper by Ravi and La Rochelle that illustrates a supervised learning, meta-learning setting. And in this setting, the way that we're going to set up the meta-learning problem is basically as a standard supervised learning problem where instead of data points, you have data sets. So the idea is that you have a meta-training set, and within that meta-training set, there are a bunch of little training sets and little test sets. And then you have a meta-testing set which has also little training sets and little test sets. And in this particular supervised learning setup, the task is image classification, and the image classes are different. So in this training set, you might want to classify, let's say, birds versus mushrooms versus dogs versus people versus pianos or something. And in this one, maybe you want to classify tanks against barrels. Fine, that's sort of what you're going to do with your life. And then hopefully you get other instances of the same classes in your test set. So you maybe have some different kind of barrel here. So here you can imagine that a good meta learner might look at these training sets and say, well, a lot of these look like object classification type problems, so I should pull out some useful features for object classification, but maintain some amount of flexibility about how I assign class labels to those features. So this is a relatively simple kind of meta learning setup in a lot of ways, but it kind of illustrates the point. And then what you can do is you can train your model, whatever your model happens to be, so that when it sees this training set, it does well in its corresponding test set. Okay, does anyone have any questions about this? Yes?
What's the metric for the meta testing?
Right, so the metric for meta testing in this particular setup is when your model sees this training set, what is its classification accuracy on its corresponding test set? And you have a number of different training sets and their test sets, and you want to do well there.
What happens if we make everything the same data set? Doesn't that seem a bit like...
Yep. Yeah, so there is a degenerate edge case here, right? You could imagine a setting where each of the training sets is like all of ImageNet, and then it's not meta learning, it's just supervised learning. So this setup is a little peculiar, the way it's illustrated, right? And part of the reason for that is that these tasks, they're in some sense not actually mutually exclusive, right? You can imagine building a single model that does all of them. The only thing that makes them mutually exclusive is our assignment of class labels. So this is meant to be kind of a toy illustration. Okay. So let's work through a simple approach that we could imagine might be used as a first cut at tackling this kind of problem. So in supervised learning, we want to build a function, f of x, that takes in some input x and produces an output y. So in this case, x might be an image and y might be a label. Now, if our data points are little data sets, now we want to train a function f that takes in a data set, dtrain, a test input x, and outputs the prediction for that test input. So it's still a well-defined function. It's now a function that operates over a set and an input and outputs an output. So the training set might be, in this case, for example, a couple dozen images. So if we want to construct sort of the simplest meta learner, the first question we have to answer is, well, how do we set up this function? And the only thing about this function that's a little unusual is that it needs to be able to read in the training set. So we need to define some kind of function. If we're classifying images, neural networks tend to work pretty well as our function representation, but they need to be able to read in an entire training set. So one way we could do this, not the only way, but a relatively simple way, is to set up something that looks like a recurrent neural network, something that can process at each time step of the recurrent neural network a tuple of a training image and a training label. And if there are, let's say, 3 training images and training labels, then you have 3 time steps, and at the 4th one, you get in just the test image and you predict its label. So there are different ways to architect this kind of recurrent neural network. I won't get into the details too much, but at a very high level, it's just some kind of neural network that can input all of the training images and the test image for which you're looking for a prediction. Now, this has kind of reduced this meta-learning problem into a very basic form where it essentially just looks exactly the same as supervised learning. But this kind of connection can hopefully shed some light on how these kinds of problems can be approached. And the nice thing is that if it is reformulated as standard supervised learning, then it's relatively easy to get a handle on how you can actually train this thing. So we'll see an approach for meta-learning in deep RL that also parallels this kind of method. Does anybody have any questions about this? OK. So yeah, this part is the few-shot training set. This is your test input, and that's your test label. OK. Now let's talk about meta-learning and reinforcement learning. So in supervised meta-learning, I said we have a function that takes in your test point and a training set. In supervised in reinforcement meta-learning, if we want to follow an analogous line of thinking, then we just need to define a function that takes in a state, outputs an action or a distribution of actions if you have a stochastic policy, and a training set, which in RL is basically your recent experience. And you can actually imagine any kind of reinforcement learning algorithm as being representable by such a function. So if you have policy gradient, well, dtrain is going to be all of the data you've seen so far. S is your current state, and you're making a prediction. And policy gradient, the form of that function is a sort of peculiar form where you're computing log pi's and advantages and so on, but it's just some kind of function. So now, one of the simplest ways to get started with a meta-learning approach for RL is to say, well, instead of having this function be the policy gradient algorithm, let's have it be some kind of learned function. And it just needs to be able to ingest your recent experience over there, this dtrain. So dtrain consists of everything that you've observed in the world, which is states, actions, and rewards. And we need some way to feed them in, so we can do the same thing that we did on the previous slide. We can say, OK, let's build a recurrent neural network instead of a policy gradient algorithm, and let's give it state, action, reward at time step 1, state, action, reward at time step 2, et cetera, however much experience you've collected. And then at the end, you say, OK, now here's my state that I'm currently at. Give me an action. And if you train this thing end to end, you will get something that looks like a meta-learning algorithm. OK, OK, so that's your experience. This is your new state, and this is your new action. Does anyone have any questions about this? Yes?
It almost looks oddly like a maximum likelihood. It just looks, it looks like behavioral cloning, though.
Right. Well, I haven't actually said how you train this thing, right? So this is just the representation. The way you would train it is with RL. So if your goal is to choose the actions that achieve the highest reward, you can then plug this whole thing into some kind of optimization algorithm that will optimize for the expected reward of these actions. So you could optimize these things directly with a policy gradient algorithm. So now we would say that the policy gradient algorithm is the meta optimizer, and this thing is representing your fast adaptation or your learning algorithm. And this is, like, if this seems a little circular, it's because it kind of is, right? Because we're sort of saying that, well, OK, any learning algorithm can be represented as this kind of function that is a true but maybe a little simplistic statement. And then we say, well, let's just throw it out and replace it with a recurrent neural network, which is, again, not an unreasonable thing if you have enough experience to train this thing. Yes?
I guess when I was thinking, like a meta-learning, I was thinking there would be like an exploration policy rather than a spitting out action. For an RNN, can we, if we formulate it as an RNN, can we spit out like a sequence of actions to take rather than just one as it's shown in, I guess, the couple of figures?
Right. So this is a very good question. What this question really gets at is the question of representational power. So if I told you that this function f could, and maybe instead of outputting an action directly, maybe it outputs a distribution over actions. That's the most general version. If I told you that this function f could represent anything. Now, policy gradient algorithms or Q-learning algorithms or whatever, they are in the class of anything, right? They are, in the end, functions. So that means that if you can represent any function, then you can represent Q-learning, you can represent policy gradient, and so on. In the sense that you have sufficient capacity. And a sufficiently large recurrent neural network is, in fact, a universal function approximator, so it can represent anything. Now, that doesn't mean that it can represent anything in any useful sense, right? In any kind of deep learning problem, and this is in general a very important point, there's kind of two things you need. You need a sufficiently expressive function, and you need to be able to train it. So we know how to build a sufficiently expressive function. That part we've known for like 3 or 4 decades. You just build a recurrent neural network, give it millions and millions of weights, and it can represent anything. That doesn't mean you can train it, unfortunately. And in fact, at the end of this discussion, I'll actually mention some of the pros and cons of current methods, and the difficulty of the optimization problem is one of the biggest challenges right now. Yes?
So just to clarify, perhaps a different way of expressing it would be FP train S goes to FS goes to A, and like the left part of like the experience is that the function, it takes both the set and the state, and then that right part is like you can consider like a feed forward network that actually like does the thing.
So you can set it up that way. That is actually a special case of this thing. If you have a deterministic policy, if you have a stochastic policy, you just need to replace this with a distribution. Because so what you described is very reasonable, but that second bit, that function that takes in the S, it can be subsumed within this structure. So in the end, the composition of the function that reads in the training set and the function that takes in the state, that composition is itself a function. So that means that we could write it as just one thing. It's not necessarily the clearest way, but it is a well-defined way. And in fact, when I mentioned earlier that there are meta-learning algorithms that learn optimizers or meta-learning algorithms that do this RNN thing, they're kind of 2 sides of the same coin. So you can imagine the meta-learning algorithm that learns an optimizer, the one that ingests the training set and then, let's say, outputs the weights of another network. It's just that process itself a different network that just happens to have a very peculiar architecture. So they're really kind of the same thing. All right. So let me give you an example of a paper that did basically exactly what I described on this slide. It has an RNN that reads in your recent experience, the current state, and outputs an action. This is a paper by Nicholas Hess and his colleagues called Memory-Based Control with Recurrent Neural Networks. I realize this looks like worms in a petri dish, but it's actually not. So let me explain what this picture is showing. This is a result from that paper. And this is what they call the water maze task. So the task here is very simple. You have a little 2D agent, a point on an infinite plane. And what that 2D agent wants to do is he wants to go into this red circle. So in the red circle, there is reward, and outside of the red circle, there is nothing. So he wants to find the red circle, but he's not told where the red circle is in advance. And the setup is the following, that every task in this universe corresponds to a different position of the red circle. So the universe begins, the red circle is placed in a random location, and then the agent is allowed some number of episodes to try to find the red circle and accumulate as much reward as he can. And what these little worm-like looking things are actually showing are the trajectories that the agent takes. So the pink trajectory is the first attempt. That is the first episode after the universe has been created. The blue one is the second attempt, and the yellow one is the third attempt. And these 3 on the left, these are the attempts made by an agent that has already been trained on many such tasks. So this agent was trained on tasks where the red circle was in a different place for every single task. And what this agent learned is that across tasks, he should keep track of his belief about the location of the red circle, and on the first attempt, he should execute a search pattern. So the first attempt looks very different from the other 2 because in the first attempt, he has no way of knowing where the circle is, so he searches around in this kind of complicated search pattern, and on subsequent attempts, he just recalls where he saw the reward and just goes right there. Whereas an agent trained using the same algorithm but without memory basically does somewhat arbitrary things on every single attempt. So without memory, he just kind of does these funny figure-8 things and sometimes stumbles into the goal region and sometimes not, and has no way of improving performance across episodes.
So without memory means without memory both in the, I guess, episode for the same location, the red circle, and also not between red circle shifts?
Yeah, this one is actually without memory at all. A very reasonable baseline would have been to actually do what you suggested, which is maintain memory within an episode but not across episodes. The notion of episodes is a little artificial in some sense because an episode just means that you got teleported back to a random location. So one might say, well, maybe that's just one way to structure your universe. In another universe, maybe you don't have episodes at all. You just search forever until you're happy. Yes?
I mean, if you don't have memory within the episode, then there's kind of like no way to optimize, period.
Correct. Yeah. So this is a fairly weak straw man. That's completely true. Insofar as there is a point to this, the point really is that it is, in fact, possible, if you have a policy with memory, to learn something that looks like a search strategy. So it's really not much more profound than that. So let's actually move on and talk about another paper. This is by Duan et al. Called RL squared, fast reinforcement learning via slow reinforcement learning. This paper does essentially the same thing, but on a substantially harder range of problems. And this might also give us a little bit more intuition about how this is supposed to work. So in this approach, and this is, I think, a much nicer illustration of how this is supposed to work, there is a recurrent neural network policy. That's what's represented up here. So H is the hidden state of that recurrent neural network policy. And then there's this notion of a trial and a meta-trial. So a trial in the, a trial and an episode is what they call it in the paper. So a trial is what the meta optimization algorithm regards as an episode. The episode is what the task regards as an episode. So in the Petri dish from before, an episode means that the agent was teleported to a random location, but the circle stayed in the same spot. A trial means that the circle has now moved to a different random spot. Memory is not preserved across trials, but it is preserved across episodes. So that means that the RL algorithm that's actually the outer RL algorithm, the meta RL algorithm that's performing this optimization, views these things, the trials, as though they were episodes. So when it propagates gradients through this RNN, it propagates from here back to here, but not across this boundary. But it does propagate across this boundary where there was an episode reset.
So each wrapper sees the trial as a different sample kind of thing.
That's right, yeah. So if you were doing this with a policy gradient algorithm, then each trial would be a separate sample, but each episode would not be. And this distinction is important, actually, to understand how this works, because that's essentially the only distinction between this and a standard reinforcement learning algorithm, is that you have to preserve your memory across the episodes in order to be able to actually retain some kind of knowledge. OK, does anybody have any questions about this approach? It's a little bit confusing, so if anyone is unsure how this works, please raise your hand. OK. So let's look at some of the experiments in this paper. They're actually quite a bit more sophisticated than the Petri dish. So the experiments that they're looking at are these little maze navigation tasks, where you actually have first-person observations in the maze. And the mazes and the position of the starting point and the goal are randomized. So in order to be able to succeed, the RNN policy here has to learn how to search through the maze. And analogously to the car example I gave before, there are certain kinds of behaviors that are just never useful. So it's never really useful to walk into a dead end and get stuck there and keep trying to walk into the wall, but it is useful to navigate in a coherent but arbitrary manner to try to find the exit. And these are some illustrations of this algorithm actually performing the search. So this is showing what happens when it sees a new maze, and this is the first episode. So remember, episodes are the inner thing, and trials are the outer thing. So this is one trial, this is another trial, and this is one episode, and this is another episode. So you can see that on the first episode, it doesn't go directly to the exit. It actually goes up here, then comes around, and then comes around like this, and eventually finds the exit. So it's executing an arbitrary but coherent search strategy. And then on the second episode, it's able to recall what happened over here and just go directly to the exit. And what this second trial is showing is that, well, sometimes it's not quite so clean, so sometimes it'll find the exit right away and then forget a little bit and so on. So it's not completely perfect, but it clearly shows some signs of actually executing coherent search strategies and then recalling from past experience the location of the exit. All right. Does anybody have any questions about this paper? OK. Now, when I discussed multitask learning before, one of the things I mentioned is these things called contextual policies. So just to remind you, in a contextual policy, if you have a multitask learning setting and your policy needs to figure out what to do, the context is what tells it what to do. So if you have a robot, it goes into your home, and it needs to know today, is it time to do the laundry or is it time to do the dishes? The context is that little piece of information that tells it, is it time to do the dishes or is it time to do the laundry? And the examples I had before were some robotics example where the context might be the location where you put a Lego block, or a computer graphics example where the context might be the direction that you walk. Right? The interesting thing about the RNN-based meta-learning algorithm that I described just now is that it can actually be viewed as a kind of contextual policy, where the context is the experience. So this policy is conditioned on some context omega, and if you make that context omega be all of the experience that you've seen so far, then you can actually see that these meta-learning algorithms are just contextual policies where the context just happens to be extremely complicated. So before, the context was something simple, like a binary indicator saying, do the laundry or do the dishes. Now the context is very complex. It's a large collection of experience that you've seen recently, but it can still be thought of as a contextual policy, which gives you, I think, a little bit of insight into what these things are actually doing. And then the policy part is just this part. All right. So now let me shift gears a little bit and talk about a different kind of meta-learning algorithm. It actually will look extremely different at first, but then afterwards I'll talk about how it's actually quite closely related to this RNN thing. So to motivate this other type of meta-learning algorithm, let's go back to ImageNet pre-training. So when I just started talking about transfer, one of the things I mentioned is that fine-tuning is a really good way to produce transfer. And in fact, in supervised learning, fine-tuning is one of the most popular ways to do transfer. So you could, for example, train a big network to classify images on the ImageNet data set, pull out features from that network, and then train some other system, for example, to localize parts of a bird using those features. So somehow, from performing this very rich task of ImageNet classification, you get some kind of representation that's useful for lots of other things. So one of the questions we might ask is, well, is pre-training actually a type of meta-learning? The thing is that when you get good features from this network that was trained on ImageNet, you can then be much more efficient and much faster about learning a new task. So in some sense, something in those features is accelerating the learning process. So in some ways, it is a kind of meta-learning algorithm. The trouble is that this kind of approach to transfer is not explicitly optimizing the features to be good for fine-tuning. So it's very fortunate that if you want to classify parts of a bird, you can grab features that were trained on ImageNet. But in some ways, it is a consequence of ImageNet being kind of a very good data set. If you're faced with some other set of source tasks, this trick might not work. So now, one of the things that you might ask is, well, can we somehow force it to work? Can we introduce a meta-learning algorithm that does try to get us features that are good for fine-tuning? And we can actually do exactly this. We can actually try to optimize for a representation that is then good at learning quickly via fine-tuning. So this is a method called model-agnostic meta-learning. And the idea is the following, that let's say that I'm trying to get this little ant to walk using policy gradient. And I'll just use policy gradient as an example, right? So in policy gradient, at a very high kind of schematic level, the way it works is you generate some samples for your ant running forward, right? And then you compute the gradient of your reward function, and we learn how to do this in the policy gradient lecture. You increment your parameters, and then you have an updated parameter vector theta prime, and then you generate more samples from that, and so on and so on. So now, let's turn this into a multitask setting. Let's say that, for simplicity, the tasks are just going to be the ant running in different directions. And we'd like to learn a good representation that allows the ant to quickly adapt to run in new directions. What we can do is we can say that, well, we know we're going to fine-tune. We're going to fine-tune with this kind of gradient rule. That's the only gradient rule that we know. So let's actually optimize our representation so that when we fine-tune on a particular task, so the subscript I here denotes, for example, the running direction of the ant, when we fine-tune on a particular task I, we achieve the largest reward on that task. And then we can compute the gradient of that reward. So this takes a little bit of thought to, I think, to kind of internalize. But what this is saying is, don't make the reward on task I high by itself. Make the reward on task I be high after you take one gradient step on task I. So you know you're going to fine-tune, so change the representation so that when you fine-tune, you do as well as possible. It is not possible to build one policy that runs that does really, really well at running in all possible directions, because the tests are mutually exclusive. You can run in a random direction, but then you'll only get the right direction a fraction of the time. So you can't optimize the reward in all the tasks together, but you can optimize the reward after one gradient step, because that gradient step gives you information about which task you're supposed to be performing. Yes?
The square brackets mean evaluating Ri at that location.
Yeah. So this is like Ri, and this is the argument to it. So I'm treating Ri as a function of parameters here. Yeah. So we can illustrate this graphically. Those of you that are visual learners, maybe this might be helpful. You can imagine this, this thick line. This is the path of the parameters theta through the parameter space. And at every point, every iteration, what you do is you compute the gradient with respect to theta for all the different tasks, L1, L2, and L3. And you're not trying to get the parameters theta to be at the optimum for any of these tasks. You're trying to get them to a point where these individual steps get them as close as possible to the optimal parameters for that task. So the parameters themselves might not actually be the optimal for any one task, but they're in a spot such that these vectors, grad L1, grad L2, and grad L3, point in the direction where it gets them close to the optimum. Yes?
I mean, is this kind of like an early stopping kind of thing? Or?
It's not exactly early stopping. So the fact that your argument to your objective is your parameters plus a gradient step is what actually makes this meta-learning. And I think that the next slide will hopefully explain a little bit more what exactly is going on. Yes?
If it wasn't for its inefficiency, if you could fully optimize that inner argument, would that be better? Or
yeah, so you could imagine just saying, OK, instead of taking one gradient step, let's take 1,000,000 gradient steps. And that would be better, with the following caveat, that if you want to meta-learn so that you can learn quickly, you probably would want to then add some additional objective that says, well, it's good to get to a good place after 1,000,000 steps, but maybe I would prefer it after 1,000 steps. Right? So in practice, actually, when people use this algorithm, they usually take a little bit more than one step. So practical choices are single digits, so like between 5 and 10-ish.
And a follow-up, if there's time.
Yeah, of course.
Wouldn't we be making some kind of assumption about the fact that there exists a theta that's so close to the solutions to all of the other RIs?
Yeah.
By making the short step thing.
Yes, this is another very good question, which is, does this involve some kind of assumption about the learning process? And let me present the material in the next slide, and then I'll come back to this. This is a very important question, actually. So let's first try to understand a little bit better what we just did in terms of the machinery that we've covered so far in this lecture. So we saw before that supervised learning, you get a function of x that gives you y's. Supervised meta-learning, and very similar to reinforcement meta-learning, it's a function of a data set in an x that gives you y's. So what the heck is model-agnostic meta-learning? Well, model-agnostic meta-learning is the same exact thing. It's just a different choice for this function. So before, we represented the function f, for example, with a recurrent neural network that ingests the data set and the test point and outputs the test label or the test action. Now, we're representing the function f with a neural network with parameters theta prime, where theta prime is given by this update rule. This is just a function. It's just a different function than the RNN we had before. So it's, in fact, closer to the kind of learning rule that we would ordinarily have, and we're just wrapping this up, plugging it into here, and training this function fmaml. So it is not actually conceptually all that different from the meta-learning algorithms we covered before. It just involves a different choice of representation for the function f. So it's just another computation graph. And in particular, that means that you can implement it with any automatic differentiation package. So in practice, you can just set this up in TensorFlow, like literally write this out in TensorFlow, call .gradients on it, and optimize it. But in some situations, we might expect this to have a favorable inductive bias because we're essentially telling this function through its architecture that these kinds of gradient update rules are a good idea for improving your performance on a new task instead of learning it from scratch. So conceptually very similar, just a different design of the computation graph. Before we had an RNN, and now we have this gradient descent rule. Now let me come back to your question. Your question was, does this involve introducing some additional assumption? Meaning, is there something that you can do with a general function that you cannot do with this function? That's really what that question means. That is actually the topic of some ongoing research, and there's actually a paper that we're actually working on, will hopefully release in the near future, that studies exactly this question, whether basically anything is lost in the representation here. So this you'll have to wait for a little bit, but in a few weeks we'll hopefully have an answer for you. Yes, there's another question?
Yeah, I mean, does this, so I mean, in the example that you gave, to motivated, you were talking about the different tasks were move the same ant in a different direction, but what about, I guess, for different, I don't know, problems besides tasks for the same robot? Is this applicable, or is this space too different?
Yeah, so the question is kind of how broadly can we go with this, right? I think that this way of formalizing the problem, just viewing it as a function of a data set, can help us understand that. So we need to be able to represent the tasks in some way that we can actually process using the kind of function approximators that we know how to build today. So if we have, for example, different tasks with different input dimensionalities, we need to figure out some way to actually process that input, and we can figure out some perhaps clever architectural designs for that. In the end, so long as you can wrap it up in a function like this, conceptually you should be able to use the methods I described, both the RNN method and the model agnostic method. Now, all of this comes with a caveat that you need to actually be able to then optimize those functions. And that's where you might start running into trouble. So building the architecture that is capable of representing, let's say, variable dimensionality inputs, we can do that. We can build, for example, an autoregressive neural network. Whether we can optimize it effectively, that's a different question. OK, so let me show you a few neat videos that I think illustrate some of the intuition behind how this algorithm works. And then I'll talk about some of the open problems in meta learning and some of the current challenges. So first, what I'll show is some videos of this ant running in different directions. And the first video will illustrate what happens if you execute the parameter vector corresponding to the point that was actually the parameters that were actually optimized with the algorithm. So these are the parameters before the gradient update. This is the parameter vector that you get if you run model agnostic meta learning, meaning that you're optimizing for the parameters that are essentially one step away from doing well on any one task. These parameters do not do well on any single task at all. But what they do is actually quite interesting. So if you actually run this policy, you can see that the ant is sort of running in place. So it essentially figured out how to discard all the things that are useful. It's not flipping over. It's not trying to do anything crazy, but it's kind of running in place. It's a neutral kind of task-agnostic behavior that's ready to learn. And then if you have one iteration of policy gradient with a forward reward, it learns how to run forward, and one iteration with a backward reward, it starts running backward. And the inner update is performed using standard policy gradient, and then the outer, the meta optimizer in this case, is trust region policy optimization. And we can do the same thing with a different system. So just to give you another example, this is the meta-learned parameters for the cheetah task that some of you hopefully tried for homework 1. And this is, again, the cheetah is running in place. And then with a policy gradient update for a backward running reward, it starts running backward. And then with an update for a forward running reward, it starts running forward. And then it does like a cool flip. So, yeah. Well, it's for fun. All right. So those are some of the results to hopefully give you a little bit of intuition for what these algorithms actually do. All right, let me go over a summary of what I covered and talk about some open problems. So meta learning, if you wanted to describe it in 3 words, refers to learning to learn. Supervised meta learning means supervised learning where data points are essentially entire data sets. RL learning can be done, RL meta learning can be done in a number of ways. One of the ways that's been explored quite a bit in the literature is to simply use a recurrent neural network for your policy so that that recurrent neural network can ingest a history of your past experience and then make predictions on a new state. And then the learning basically just consists of executing that RNN. So meta learning means training the RNN, and learning means just running the RNN. And we talked about how these are basically, these can also be viewed as just contextual policies. So there's kind of 2 equally correct views. One is that it's meta learning, and the other one is it's just a contextual policy with a really complicated context. In which case, there isn't actually any learning, and which view you subscribe to, they're both correct. It's just a matter of how you want to look at it. Model agnostic meta learning uses gradient descent as the learning rule. But conceptually, it's actually not that different. So even though when I presented it, I motivated from a very different standpoint, talking about representation learning, you can, again, equivalently recast it as just a different design for that function f that takes in the data set and the state and outputs the action. So you can say, well, maybe this thing is also just contextual policies, just with a really bizarre design for your neural network that has this gradient rule in it. But you might say, well, if that gradient rule is actually useful for adaptation, maybe it's injecting favorable inductive bias. So just like with the RNN policies, there's sort of two views. One view is that you're optimizing for a good representation that adapts quickly, but the other view is that, well, you're just doing the same thing that you did here, just with a different architecture. And again, both views are correct. All right. Now let's talk about some of the, the good and the bad news. So that was what was done in the literature. Now let's talk about what are some of the limitations and some of the problems. So the promise of meta-learning is to use past experience to just acquire a much more efficient deep RL algorithm. So the promise is a very lofty promise. It's saying, well, don't bother designing better algorithms, just collect lots of experience of all sorts of random tasks, run meta-learning, and you'll get something that will just work very, very quickly. The reality is that the current meta-learning methods we have are still in their infancy. So they mostly work on smaller problems, and both of the classes of RL meta-learning algorithms I described have pretty severe limitations. But they're getting better all the time. So what are some of the limitations? Well, with the RNN policies, one of the really big problems is that RNN policies are extremely hard to train. And they're especially hard to train when you need to maintain memory over a long period of time. So that D-train, that data set that you have to ingest, if it consists of maybe 100,000 state transitions, maybe you want to learn a very complex task, your naive RL algorithm requires 10 million transitions, and you'd like to learn 100,000 transitions. That's still a very big improvement. That's a 3 order of magnitude improvement. The trouble is that you can never train RNN with current technology to ingest 100,000 data points and still be able to propagate gradients all the way from the back to the front. Simply as an optimization problem, right now it's just a bit too hard. Model-agnostic meta-learning avoids the need to backpropagate through time like this. You don't need to backpropagate through time into all of your data points, but it still presents a very tough optimization problem, partly because it's computing the second derivative when it computes the gradient of the reward after one gradient update. So it has also a tough optimization problem, a different optimization problem than the one for the RNNs, but still difficult. Now, these are the optimization difficulties, and those are actually not even all of the difficulties. The other difficulty is that designing the right task distribution for meta-learning to be effective is hard. In fact, this should come as no surprise. In regular supervised learning, we already know that the distribution of training points matters. The standard assumption in supervised learning is that your test points are drawn from the same distribution as your training points. If your training and test set have non-overlapping support, you have no guarantee of doing well in your test set. If you trained, for example, to classify dogs on grassy fields, and now you're testing your algorithm on classifying dogs in houses, there's no reason for your algorithm to work. Maybe on the grassy field, it was using something about the shadow of the dog on the grass to figure out what it is, and the house, maybe that's no longer working, right? If you change your distribution, there's no guarantee of learning working. And meta-learning is exactly the same way. If you change your task distribution, there's no guarantee for meta-learning to do anything even remotely sensible. And in practice, what that means is that designing the right task distribution is hard. And generally, these kinds of algorithms can be very sensitive to task distribution design, which you can view as a kind of meta-overfitting. So overfitting means overfitting to data points. Meta-overfitting means overfitting to training tasks. OK, so that's it for meta-learning. Does anybody have any questions before we conclude? Yes?
Do we have any way of understanding which learning algorithm the recurrent neural network has learned in the meta-learning task?
Mm-hmm. Yeah, so the question is, can we understand what kind of procedure the meta-learning actually learned? It depends very much on how you represent that function f, right? So the RNN representation is in some sense one of the most black boxy kind of representations you can come up with. It's a fairly opaque neural net, and it does some kind of processing on the data set and then spits out an answer. So I'm not aware of any work that has actually tried to analyze what exactly it's doing in there. The class of meta-learning algorithms that learn optimizers, so I mentioned 3 classes, learning optimizers, learning RNNs, and then learning representations. The class that learns optimizers, to my knowledge, there hasn't been very much work in RL on that, but those might be a little bit more interpretable, because there you might actually look at how it's changing the weights. There's another line of work, and I mentioned this also at the beginning of the lecture, that I called meta-optimization, which is also often called meta-learning, that deals with optimizing, actually not directly optimizing the learning rule, but optimizing some aspect of the learning rule, like a learning rate. And there's actually some interesting work on doing things like trying to actually optimize over a parametric form of an update rule. Instead of spitting out the new parameters directly, you actually optimize over the parametric form of an update rule, and you actually pick basically the mathematical expression. And there you can actually look at what it does. So if you want to learn more about this, I highly recommend some work by Kwok Lei at Google Brain, who's used stochastic optimization algorithms to optimize parametric forms of update rules. Yes?
Going back to the, okay, so this might be a little bit too detailed, so I guess you could stop me if it gets too much. But going back to the slide you showed, the model agnostic meta learning, sort of the policy that it had as the starting point that could. I noticed that like in the case of both the ant and the dot and the like cheetah, like it was sort of like jittering around, like jumping around a little bit, and it looked sort of like you were saying, like running in place, but it still looked sort of unstable kind of thing. And I wonder if you had experience with maybe trying to encode some sort of extra criterion of like, and also be stable, have a stable limit cycle in this, and then like see if that puts you in a better parameter spot for generalization.
That's a good question. I'm not aware of any work that has tried to do any kind of regularization of this sort for meta learning algorithms, but I think it would be a good thing to try. Yeah. Any other questions? Okay. So next I'll talk about parallelism in RL. So before we shift gears, let's take a short 2-minute break. So we'll resume at 11:32. All right, let's continue. So the second half of today's lecture is going to be on actually a pretty different topic because towards the end of the class all the miscellaneous topics get kind of squished together. But this is a very important topic, and actually parallelism in reinforcement learning is an active area of research, especially when it comes to applying reinforcement learning algorithms in simulation. It can be very, very important to get good performance and to get your answers quickly by making use of parallelism. So we learned about a number of different policy search methods in this course, and so far all the algorithms we've talked about have actually been sequential, although in the actor-critic lecture I very briefly alluded to parallel algorithms. In this portion of the lecture I'll actually get into that in a lot more detail. So we're going to talk about whether there's a natural way to parallelize RL algorithms. I'll talk about how there's different parts of an RL algorithm that can be parallelized, collecting the experience, learning, having multiple learning threads, multiple experience collection threads, and so on. We'll talk about what we can parallelize. We'll talk about some specific parallel RL algorithms in the literature, so we'll have some case studies. We'll talk about the different trade-offs and considerations there. And our goals will be to understand the high-level anatomy of parallelized reinforcement learning algorithms, building off of the kind of flow chart that I had actually in the beginning of the course, and then understand some standard strategies for parallelization. and the trade-offs between the different methods. So let's go back to the schematic that we had earlier on in the course, where we talked about how for pretty much any RL algorithm, you can break it up into 3 parts. You have the part where you generate some samples, which typically involves running your policy, for example, in a simulator or in your real system. We have some part that involves fitting a model or estimating a return. And then you have some part that involves improving your policy. And for pretty much all the algorithms that we had covered in the course, they had these 3 parts, although sometimes one of these parts was kind of very, very simple. So for instance, in a model-based RL algorithm, fitting the model might literally mean like fitting the model, fitting the dynamics model of P of S prime given S comma A, which involves running some pretty heavyweight supervised learning method. In policy gradient, fitting a model basically just amounts to summing together your rewards. So it's just a summation operation. There's no fancy learning there at all. It's just evaluate your return. So, and then in like something like actor critic or Q learning, it might also involve fitting a neural network, but not a predictive model. Instead, it fits a Q function. Improving the policy also sometimes is something very complicated, like optimizing your model in a model-based RL algorithm by backpropping gradients through your dynamics. And sometimes it just involves taking a gradient step, like in policy gradient. So this is the diagram that we saw before that we were hopefully all familiar with. And now let's talk about which parts of this diagram are problematic, which parts are slow, which parts can we think about accelerating. The orange box, you know, it can be either very fast or very slow. So if you're running on a real robot or a real car or a real power grid or whatever, if it's a real physical system, it's going to be running at 1x real time because we don't have time travel. So that's the best you can do. And this thing might actually be a really big bottleneck. If you're running the Mujoko simulator, okay, the Python wrappers are a little clunky, but if it wasn't for the Python wrappers, you could probably get something like 10,000x real time out of that thing. So there, you're probably not worrying about your simulation speed. So depends very much on what task you're doing. This can either be a really bad bottleneck or a complete non-issue. So we'll talk about, you know, if you have this case and you need to actually do parallelization, how should we do that? When you're fitting the model, again, same thing. If you're doing policy gradient and you're summing together rewards, you don't even think about this thing. This thing is so cheap, it hardly matters. If you're fitting a Q function, well, that might actually take a little bit of time, especially if it's a Q function like in homework 3 that's actually processing images represented by a convolutional neural network. Maybe it's actually quite expensive. It's a little non-trivial to parallelize, but there are actually some tricks you can do to speed that up. If you're improving the policy, well, if you're doing Q learning and you're just taking this max, it's really not a big deal. We usually don't worry about it. But if you're optimizing the policy, for example, in a model-based RL algorithm where you're actually pushing gradients through a big neural network, through your dynamics and so on, again, it can be quite expensive, and you can imagine some algorithms inspired by parallel and asynchronous stochastic gradient descent that could greatly accelerate this phase. So the point is that depending on which algorithm you're using and which problem you're solving, different parts of this flowchart might be the bottleneck. Different parts might be very, very slow, or they might be trivially fast. So what can we parallelize? Well, we can parallelize the generation of samples. If we're collecting them in the real world, we can parallelize the real world by having multiple physical systems. That's expensive, but quite doable. If you're running in simulation, you can parallelize much more by using lots and lots of compute. So we'll talk about ways that we can get parallelism there. You can parallelize fitting your model using, for example, parallel SGD. And you can parallelize improving the policy using other variants of parallel SGD. So actually, all of these parts can be parallelized depending on what you're doing, and they can be parallelized in different ways. OK, so some high-level decisions to keep in mind when thinking about parallel reinforcement learning. One decision that's going to greatly affect the design of your algorithm is whether your algorithm is online or batch mode. So what I mean by that is in an online algorithm, you're basically making updates to your network, whether it's a policy or a Q function, as fast as you're collecting data or faster. So Q learning falls into this category. You take one step of simulated experience or real-world experience, then you update your Q function, you take one more step, and then you update it. And you can, of course, decouple these into separate threads. Batch mode is more like how, for example, policy gradient works, where you collect a big bucket of experience, update on that experience, collect another big bucket, and so on and so on. A second high-level decision that's important is whether you want to be synchronous or asynchronous. Asynchronous is not synonymous with parallel. So you can be parallel but synchronous, which means that you can actually come up with algorithms that are parallelized but are mathematically exactly equivalent to the original serial algorithm. You can also build algorithms that are asynchronous, and these asynchronous algorithms might actually be different in terms of the solution they get to and their convergence rate than the original synchronous algorithm. So here are some very straightforward kind of examples. This is a way to parallelize policy gradient. It's not the only way, it's a very simple way. So in policy gradient, you collect a bunch of samples, a bunch of trajectories, and then you compute the gradient and update your policy. So the collection of the individual samples is completely independent from each other, which means that you can do them all in parallel. And then you can put a synchronization point represented by this green bar, and then use the data to compute your policy gradient. So if your sampling is very expensive, parallelizing the samples is a very natural thing to do. And this is now an instance of a batch mode synchronous algorithm. It's parallel, but it's synchronous. And in fact, this algorithm is mathematically exactly equivalent to standard policy gradient. You could imagine a Q-learning algorithm where you have multiple threads that are all collecting experience. They all generate one time step of experience, which is then fed to multiple threads that are all fitting Q values. So these multiple threads might be implementing parallel SGD, and these might just be collecting parallel experience. And maybe now there is a synchronization point here, so you don't take the next step until all of these threads have finished updating the Q function. Now, this algorithm is online. It's also synchronous. It is not equivalent to original Q-learning because multiple steps in the simulator are done in parallel, which is not the same as if you had updated your Q function between every single step. But this one is still synchronous. You can drop the synchronization point, and then it would be asynchronous. OK, so before we get into the specific algorithms that are actually used in practice for parallel RL, let's talk about the relationship between this and parallelized SGD for supervised learning. So we had these steps fit a model and estimate the return. So for both of those steps, typically, if we want to parallelize them, they're training some kind of deep neural network model. Parallelizing them typically involves parallelizing stochastic gradient descent. And it's very simple to write down a synchronous parallel SGD algorithm. So in a synchronous parallel SGD algorithm, you would have each worker, so each thread, would have a different slice of data. This is a picture from a paper on parallel SGD. So each of these workers, represented by the letter D here, they each maybe have a different slice of the data. They have a different batch. They compute gradients on their batch, sum those gradients together, and then send those gradients to a parameter server. The parameter server then sums together all of the things coming in, so it gets just one gradient, applies that gradient to the parameter vector, and sends back the updated parameter vector to all of the workers. So this algorithm, you can, if you want to naively implement it, you can implement it so that it is exactly mathematically equivalent to regular SGD. It's just that your batch is now spread across multiple worker threads. But this is not asynchronous. And in particular, this way of parallelizing SGD is often not actually very efficient because you end up incurring quite a bit of overhead from the communication delays. So while your workers are sending their gradients over to the parameter server, everybody else has to wait. The parameter server has to collect all those gradients, send back the updated parameters, and if there's one straggler, then everyone has to wait for them. Or you drop that straggler and ignore their gradient, in which case you're missing part of your batch. So asynchronous SGD is where you just don't do that. You just drop the synchronization. So you have all of your workers sending you gradients whenever they want to. You apply those gradients immediately to your parameter vector, and you send back the updated parameter vector. And you don't care about the fact that there might be other workers in flight who are working on an old, stale parameter vector. And you hope that those delays are not so big that they would actually screw up your optimization algorithm. Asynchronous SGD does not achieve perfect parallelism. There is something that is lost from the fact that you have these workers potentially operating on old, stale parameter vectors. But the lack of locks can, in practice, make it a lot faster. But it's somewhat problem dependent. OK, so here's let's work through a simple example of a parallel policy gradient algorithm. So in a policy gradient algorithm, you collect samples by running your policy n times. You compute the reward of each each trajectory, sorry. Then you compute the gradient along each trajectory using the likelihood ratio rule that we derived in lecture. And then you update your parameter vector. So one of the ways that we can parallelize it, we basically have these 4 steps, step 1, 2, 3, and 4, and we have to figure out which of the steps we're going to parallelize. A very, very simple thing to do is to just parallelize step 1. That's what I had in the example before. That is very, very easy because the samples are all completely independent of each other. But in fact, step 2 is also independent. So if you have some complicated reward function, you can evaluate that in parallel for all your samples also. And furthermore, step 3 is also independent for all the samples. So the computation of the gradient along each trajectory can also be done entirely in parallel without losing anything, and then you can sum up the gradient and then apply it to your policy. And this is essentially the synchronous parallel SGD analog of policy gradient. So this is basically exactly this thing, but now in policy gradient land. Now what if we had a critic? What if we want to do an actor critic algorithm instead? Now in an actor critic algorithm, you collect your samples, you evaluate the reward, you update your advantage with some kind of regression problem. So we talked about different ways of evaluating the advantage. I won't get back into that, but there's some kind of function approximator lurking underneath this A hat. Maybe it's a value function or Q function or something. And then you compute your gradient using the advantage. And then you sum together the gradients of all of your trajectories and apply them. So let's talk about this thing. Steps 1 and 2, we already know those are easy to parallelize. There's no problem. Step 3, the critic gradients, those can be parallelized across the different samples, and then they can be accumulated to update the critic. But now it comes time to update the policy. So the policy gradients can be computed in parallel across all the samples, but they need access to the critic. So now this is actually after the synchronization point. And then they need to be synchronized again to give you the policy gradient. So because you're using the updated critic to evaluate the policy gradient, this introduces this really problematic and expensive synchronization point where you have to wait for all the critic updates to finish and synchronize before you go and evaluate your policy gradients. This tends to be kind of a problem. So in practice, and it's not John's actor critic lecture, it was actually my actor critic lecture this year, but in practice, you would actually typically not use that synchronization point. You would simply drop it and do that nasty asynchronous SGD trick where you simply have your parameter server sitting here, sending you back parameters whenever it will, and somebody over here might actually end up using a stale critic parameter vector. And you hope for the best, that this doesn't incur too much trouble, and in practice, you end up with, computationally at least, a much, much more efficient algorithm if you simply drop these synchronization points. But now what's happening here is that the policy gradients would very often actually use an older critic to update themselves. If you do this, you can, of course, also run it online. You can simply collect your samples one step at a time. For every sample, evaluate your reward, update the advantage, and so on. So this is just exactly the online actor critic that we covered in lecture. And the only parameter update that actually requires synchronization would be this one. So let's talk about a particular algorithm now that's essentially what I presented, that has actually been used in the literature and is actually quite popular, which is called A3C, Asynchronous Advantage Actor Critic. And this is basically the asynchronous SGD of the actor critic world, rather than the just policy gradient. And the setup, very simple. You have multiple worker threads. Each of the worker threads collects experience, updates their critic, updates their policy, and then sends the updated parameters to the parameter server, which applies their gradient and responds by sending back the updated parameter vector. And after this happens right here, this thread is still using some old parameter values to finish collecting its experience and update its gradient. This thread is also using some older parameters. But as soon as this thread finishes, it sends back its gradient, receives back the latest parameters, and now it's got the latest parameters. So this is basically a synchronous SGD, but in the world of actor critic methods. So there are a number of interesting properties of this algorithm. One of the properties is that, as with all asynchronous SGD, these gradients are sometimes collected using somewhat different parameters than the ones that are currently the freshest on the parameter server. And while this is typically a bit of a problem in asynchronous SGD methods, in RL it also has a little bit of a potential benefit, which is that you're collecting experience with slightly different parameter vectors. And that means that you're getting a little bit of more variety of exploration, kind of similar to a very informal method, or a very informal version of the bootstrap DQN that we covered before. So if you have slightly different parameters, you're getting slightly different structured exploration among the different worker threads. And this can, in practice, actually accelerate learning a little bit on tasks that have a bit of an exploration challenge. Generally, this algorithm is substantially faster in terms of wall clock time than running a fully synchronous or serial algorithm. But in practice, A3C tends to be quite a bit slower in terms of the number of samples that you need. So it's, even though it's a very fast algorithm in terms of wall clock time, if you have cheap simulation, in terms of sample efficiency, it's actually one of the worst algorithms that you can use. So if you have fast simulation, you have parallelism, it's a great choice. So some plots from the original A3C paper. These are evaluations on Atari games, and the yellow line is the A3C algorithm. And in this experiment, what they're mainly trying to evaluate is this exploration benefit. So for the same training time in hours, they're doing better, and in some games, they're actually doing better even asymptotically. So in Space Invaders, this thing is improving, whereas the others have kind of plateaued. And the hypothesis in the paper about why this benefit happens is because of the exploration effect of having different workers with slightly different parameter values. But when it comes to sample efficiency, it's not such a great story. So this is a different paper that also evaluates A3C. And this is the cheetah environment. Basically, it's very similar to what you had in homework 1. And it's about like 20 million steps for it to start improving. So it converges after like 80 million steps. So quite a lot compared to something like DDPG, which can actually learn a very good cheetah running gait in less than 500,000 steps. So it's 1 million steps here, but it's already converged. So pretty large hit in sample complexity, but in practice a substantial benefit in wall clock time, and sometimes also a benefit in exploration ability. We can parallelize model-based RL algorithms. So here I'll go through an example of a parallelized guided policy search algorithm that also appears in the literature. You can say that, okay, we're going to collect n samples tau I by running different local controllers. So this is, if you remember from the lecture on guided policy search, you fit local dynamics models. For each local dynamics model, you have a different local controller. And you can, of course, run all of those in parallel. You can fit all of your dynamics models in parallel for all of your workers, and then perform the trajectory update, the local trajectory update in parallel. And then update the policy by actually accumulating the gradients from all the experience collected by the different threads when optimizing these local policies. So a standard kind of guided policy search algorithm has this sort of architecture where you generate some rollouts, update your local policies, update the global policy with supervised learning, and then repeat. And you can parallelize all these stages, and you can get in a parallel version where you can have all of your workers executing rollouts, updating local policies, et cetera, all in parallel. And you can, if you then also parallelize the global policy optimization with asynchronous SGD, that can actually run in the same worker thread. So then the only thing that's actually being accumulated, just like in the async SGD examples before, are the parameters from these global policy optimizations. So here's a video of that algorithm running on, in this case, a number of different robots. So each robot actually has a different computer attached to it, and each computer is actually running a completely separate trajectory optimization procedure, dynamics fitting, and computing gradients on that experience. And then it's just the gradients that are then sent to a centralized parameter server that applies them to a single global deep neural network policy. So all the robots here are learning to open different doors. And the benefit there is not just the speed, is actually also the diversity, that you can put a different door in front of each robot, and they'll hopefully generalize a little bit better from having seen a number of different objects. Here's another example of a parallelized, in this case also asynchronous reinforcement learning algorithm. This is based on the NAF method, which, if you recall from the Q-learning lecture, is essentially Q-learning for continuous actions, where you use a quadratic function approximator to represent the Q function, quadratic in the action, so that you can maximize it analytically. So these are just the equations from the continuous Q-learning portion of the lecture before. And the way that this particular paper parallelized this algorithm was by saying that we'll have multiple experience collection threads. So here they're mainly just concerned with parallelizing experience, and they say, okay, the experience is our bottleneck because we're going to run at 1x real time, and we're going to have just one training thread that's going to pull data from a replay buffer that multiple experience collection threads are pushing to. And the experience collection threads in this case are also attached to different robots that are trying to pull on different door handles. And then what this kind of stuff is getting at actually is that when you do have that 1x real-time constraint, one of the simplest things you can actually do for parallelism, if you have an off-policy algorithm, is just parallelize the data collection. And the better your algorithm is at handling off-policy training, the more trivial all this parallelism becomes. So that in the extreme case, if your algorithm is fully off-policy, your parallelism basically just consists of running multiple systems, collecting data, and just pushing it to some file server somewhere. And there, you don't even worry about how you design the parallel algorithm. So this is taking this idea to the extreme, where if you have many, many different systems, maybe you have many different autonomous cars on the road, or you have many different robots grasping objects. At this point, they're not even thinking about how they're going to update the policy. They're just collecting experience and pushing it to a server somewhere, running whatever reasonably recent policy they can get their hands on. And then the algorithm just amounts to many, many different workers pushing samples into a big bucket, and then some other completely separate process pulling data from that server and then training on it. So if you have a sufficiently off-policy algorithm, many of the intricacies in this lecture kind of go away, and you just have to have a big enough place to store your files and enough physical systems to collect your experience. Okay, so that's it for today's lecture. On Monday, we'll have actually the last lecture that the core staff will give. It'll probably be me and Abhishek Gupta. And then starting Wednesday, we'll have guest lectures, starting with Igor Mardac. So please do make sure to attend the guest lectures. It'd be great if people actually show up in person in class to ask questions and interact with the speaker. So see you all then.